Here's another related rates problem. So let's assume that we have this triangular trough that is being filled with water at a rate of 6 cubic feet per minute. The dimensions of the trough, well, it's 12 feet wide or long. It's 3 feet across, and it is 3 feet from the very middle of the base of the triangular sides to the bottom. So it's 3 feet deep in the deepest points. And the sides of each ends are isosceles triangles. So what we have is we have the volume of this particular trough equaling 1/2 the total length times the width times the height. So this particular trough would be 36 cubic feet. So at 6 cubic feet per minute, it should take 6 minutes to fill up, just to give you an idea. All right? But that part's really not that important. Okay? So what we're dealing with in this particular problem is what's happening when it is 1 foot deep. All right? So the volume of the water, not the trough itself, the volume of water that is in this trough is, again, I did it again, 1/2 times the 12 times, and I'm going to get really kind of intricate in here, this width over here changes as the depth of the water changes, and so does the depth of the water, okay? So those are my two variables. I have the width, which we're going to call the base of the triangle, and the height of the triangle. So really, what we're doing is we're looking at just the water in that trough, okay? And we have the base of that water, which would be this line, and we have the height of that water, which would be that line. Now, the way this works out with this particular trough, those two numbers are equal. So let's change it from B into H so that we now have one less variable. So we have V equals 1/2 of 12, which is 6, and then we have H squared. So we're going to differentiate implicitly. So we get dV dt, because we're doing it in respect to time. And I get 12H, and that's dH dt. And what I'm trying to figure out, again, we're starting at 1 foot here. I'm trying to figure out how fast is the depth of the water changing when it's 1 foot deep. So this is that value, okay? So if I divide both sides by 12H, so divide by 12H, H being the height of the water, and I remember that, hey, this value, the rate at which the volume is changing is 6 cubic feet per minute, so I have 6 over 12H. And since H is 1, I get 6/12, or 1/2. So I get 1/2 of a foot each minute at that particular moment. Okay? So if it was a little bit deeper, let's say we are getting really close to the top. Let's call it 2.9. We're worried about the overflow. So let's say, hey, what if the height or the depth of the water was 2.8 feet? Well, guess what? I'm still going to use this formula. So I have 6 over 12 times 2.8. And I'm getting 179 feet in every minute. So it only has 2/10 of a foot to go. So in 1 minute, it will be just about full. So I better shut off the water. And that's another related rates problem.